I think we're going to get started. Good afternoon. My name is Gary Baldwin, and I am with CITRIS, the Special Projects Director for Energy and Environment, also Managing Director of I4Energy, which is the sponsor of this series, along with my colleague, Gay Yi, from the California Institute for Energy and Environment. We've been hosting these seminars now for several semesters, and would like to welcome you this afternoon to this one. And welcome to our video audience. The program is being webcast, especially to our sister CITRIS campuses at UC Santa Cruz, Davis, and Merced. I would like to thank the California Institute for Energy and Environment for supporting and sponsoring these conferences, these seminars, and I hope that you are enjoying their food this afternoon here in Berkeley, at least. Today we are very privileged to have a very distinguished speaker, friend and colleague, Steve Selkowitz from the Lawrence Berkeley National Laboratory, just a few hundred yards up the hill from where we're located here in Berkeley. Steve is the program head of the Buildings Technology Department at the lab, where he heads a group of architects and engineers and scientists who are studying all aspects of thermal and daylighting performance of glazing materials and window systems and many other aspects of building energy management and control. And that's what Steve is going to talk to us about this afternoon. Just a few more words to say that a major theme of the group's activities has been to convert fenestration, that is window treatments, from an energy cost to a net energy benefit, while taking into consideration human comfort and productivity and so forth. Steve, prior to joining the lab, has worked as an energy consultant and an educator. He has a degree in physics from Harvard and a Master of Fine Arts in Environmental Design from the California Institute of the Arts. So please join me in welcoming Steve Selkowitz as our speaker today. Steve, thank you very much.
Thank you, Gary, and pleased to be here. See a few friendly faces and some new faces, which is great. So actually, as Gary said, I've been toiling up above the hill here, a couple hundred meters up the road there for over 30 years, actually. And I'll say that it's great to see the enthusiasm and the energy about energy now that's been missing for a long time, which is, I think, why the country is in the state that it's in, unfortunately. We have a group of about 400 people at the lab that worry about, and we're the applied science side of the laboratory. The laboratory, as most of you know, is a home of basic science, and 11 Nobel Prize winners. There have been about 300 to 400 of us toiling away on these applied science problems. The buzzword I heard recently was use-inspired research, which describes what we do. But about 250 of the 400 people work on buildings. So we have quite a team, one of the largest buildings research teams in the country of the world, and it's been enhanced over the years by all the partnerships with staff and faculty down here on campus and in other places as well. And I'm going to show you a lot of stuff here quickly. Obviously, it's not my work alone. It's going to be partners up at the lab and other places. I'm going to give you a flavor of the range of things that we do, because it's quite broad, a little bit of insight into why we do it and what we're looking for in terms of getting out, and with the idea of hoping to maybe create or stimulate some interest here in forming further partnerships and collaborations. And there'll be a science piece, but there's a kind of a business and applications piece here as well. So let me give you a tiny bit of history here. So this is me in junior high school, and I just want to show you that I was into low carbon energy a long time ago. This is when nuclear power was supposed to be too cheap to meter. And then I got it figured out in college, and here I am in the upper right with, hair down to my shoulders and a long beard. This is in the 70s, 76. I was teaching at an architecture school, and we did a project here. This is the 100-page booklet, which is to develop a community that lived off the grid. I mean, it developed its own energy, it grew its own food, recycled its own waste and water. It had an energy monitoring system on the lower right there that displayed for the owners what the unit was doing so that you knew what it was doing. So this is only 35 years ago. So a lot of the ideas that we're talking about here aren't exactly new. That that doesn't mean that they're bad or useless, but I think it's also useful to go back and look at what people have been doing or have done in the past and ask questions about why none of this made any difference for the last 35 years and what we can do differently now that might change that. So I think, I'm sure most of you at this point sort of know the big picture energy here, or the big picture for buildings that, actually, did I skip one there? No, I decided not to use it. Buildings are the largest and fastest growing end use of energy. And if you look at the electricity side, there's lots of talk about smart grids and everything. On the electricity side, they're over 70% of all the electricity used. So when people talk about the smart grids, they're typically talking about power plants and transmission lines and sensors and networks and all that. When I think about the smart grid, I think about where it's all going, which is buildings. And the other thing is that if you look at the right-hand lower right there, it would be nice if there was one thing that we could invent or develop and would, quote, solve the building energy problem. But there isn't. And this breaks it down by residential, commercial, it breaks it down by end use, and you see that there's about 20 different end uses that constitute probably 80 or 90% of the energy used in buildings. And if you're going to make a big dent in that energy use, you're going to have to address all of those. This is a slide from McKinsey that you've probably all seen before. Cost of carbon and the savings on the horizontal scale. And the ones on the left, the ones below the line, are the ones that pay back. And what's intriguing about this is not the data, because quite frankly, I can show you studies from 20 years ago that look a little bit different that say the same thing. The way I look at this is, if this is real, and I think it is in terms of the data, the stuff on the left shouldn't exist. If we're economically rational beings, and this stuff has 1 and 2 and 5-year paybacks, why does it even exist? And it also tells you that it's not enough to simply come up with the technical solutions. You need to figure out what those obstacles are and those impediments to the marketplace. Otherwise, we'll simply grow the curve on the left there even larger. So if you look at the building sector, you come away quickly with this is a kind of a messy, complicated set of things to be looking at. There's a complex decision-making process. A lot of people are involved. There's a lot of money involved, which makes it complicated. There are long lifetimes involved here. And the industry is fundamentally fragmented. You go to 2 owners of identical buildings. One owns it, one leases it. You get completely different responses and levels of interest. The bottom line, though, is the savings potentials are huge, and that's what we need to pay attention to. Sometimes people say to me, well, okay, what is it we should do? How do we approach the problem? Who's in charge? Who needs to take ownership of this? And the answer is pretty much everybody. This is the classic. If you ask an architect what the energy problem is, you get one answer. If you ask a researcher what the problem is, you get another. And they're all right, and frankly, they all have to work together to make this work. Now, you can ask the question, is there evidence that if we do something, it will matter? And this is a chart I'm sure many of you have seen before. It plots the electricity use per capita in California and the country. And you don't have to be a rocket scientist to say that California is doing something different here. Something has changed. And it is interesting to go back and look. And there's a lot of subtleties here, and there's plenty of work here for probably to dig in and do multiple theses over time. But the bottom line is that California has a policy to reduce energy use as much as possible. And it's backed that policy with investments in research and deployment and a variety of other activities. Now, I would argue this is a good news, bad news graph. The good news, of course, is it's flat and it's different than the U.S. The bad news is if you look at absolute energy, it's grown by 30 or 40% because the population of the state has grown. So we need to be careful here. This is per capita. It's not absolutes. And what we're trying to do in the carbon world is to reduce absolutes. Now, California continues to be aggressive, and it's a model for the rest of the country in many ways. They've developed a series of goals to 2025 and 2030. I'm going to talk a little bit about this zero energy building goal in a second. These are the right kinds of goals, but these are very aggressive. I mean, I don't think in the real world today, in the environment we live in, that these are achievable goals. Technically, they could be achieved if we put our minds to it, if the politicians decided they wanted to do it. It could be, it could happen. If I look at Washington and look at the healthcare debate, I get a bit frustrated and sort of pessimistic. But anyway, let's go on to more exciting things. So the questions of can you make a difference again? Can you do something that makes a difference? This is a chart from some of my colleagues looking at the energy use in refrigerators over time. The blue chart shows the energy use. It rose almost linearly from the 40s or 50s up to 1973, and then all of a sudden something happened in 73 and it tipped over and went down almost as fast as it went up. What happened was a whole series of mandates, of standards were put in place first by the state and then by the feds. Now the interesting thing is there's two other plots here. The red plot shows the size of refrigerators, and you see they were increasing for a while, and you could argue that the reason that the energy use went up was because they were getting bigger. There's a little moral there, too, that if you extrapolate anything, I think I once did the calculation, in 2200, refrigerators would be larger than houses. So it sort of makes you think about, you should be careful about extrapolating trends, right? It levels off because you can't get them through doors anymore. Once you can't get a fridge through the door, the size levels off, more or less. But the intriguing point here is the cost. Look what happened to the cost. We provided a 2/3 reduction in energy use while reducing cost as well. So the thought you commonly hear, which is, okay, we can save energy, but it's always going to cost more. It doesn't have to if you know what you're doing and do the right stuff. Here's some other evidence from a National Academy study that was done about 10 years ago. They went back and looked at research from the 80s, and they looked at 4 or 5 different things, a number of which we were involved in: window coatings, ballast for lights, the appliance standards I just talked about. And they calculated the market impacts and the savings, and they also went back and looked at the R&D investments. And to oversimplify a bit, these were investments, R&D investments, on the order of tens of millions of dollars, and they delivered savings at the levels of tens of billions of dollars. So if you're a country or a state and you're making investments in research, if you get even a few of them to have big payoffs, as was shown here, they more than pay for the entire portfolio of activities. So here's the challenge for the country now. Gone from the state and refrigerators to the country and all energy use. The blue line is actual energy use, total energy use for the country up to 2005. The red line, by the way, starting in 73, is what we would have used had we continued to use energy at the same rate before, if you do energy per unit GDP. So again, the good news is that we've slowed the rate of growth, but we're still growing. And if you look at the right, these are various requirements at state and federal levels to reduce energy to either 1990 levels or by 50% or by 80% out in either 2030 or 2050. It's a lot more complicated than this. Some of these requirements are carbon, not energy, and that adds another dimension to the problem. But the point I want to make is that all of these mandate reductions in absolute energy use, and we've never done that before. Well, we've never done that at the societal level or the sector level. I just showed you that we did it at the refrigerator level. So there's a real challenge and an opportunity. One of the things we've done is we built models, business models, or economic models, and energy models of the building stock. This is one of the commercial stock. And we can plug in scenarios here over time. Here we go from 2010 to 2030. Of new buildings, retrofits, renovations, the degree of savings in each one. We can add some PV if we want to, and then on the right, you can see what happens as a business as usual, which is the dotted line, and then you see we've actually managed to make the energy use of the commercial sector bend over and decrease in absolute terms, and by playing with charts like this, you can begin to get a sense of what you need to do, either technically or policy or both. So here's an example of let's say you implemented this as a policy. New construction saves, or half of the new buildings built save 50%, and every year you retrofit 10% of the buildings and you save 50%. It's a whole other discussion about whether that's feasible or practical. But this is the resultant curve. It shows a decrease for about 10 years and you meet the 2020 goal, but because you're not aggressive enough in new construction, it rises over time in the end. Here's a scenario that actually gets you to this amazing 80% reduction goal by 2050, but this is a sort of a superhuman effort that basically all new and existing buildings are using only 10 or 20% of what they're using now. But it's an interesting tool to give you a sense of the magnitude of what you need. So this concept of a zero energy building, a net zero energy building, some people take it literally that, if you take a building and you put enough PV on the roof, then you bring the energy use down to zero. A net zero building is a building that generates as much as it uses, therefore its net impact is zero. So there's a group out there that says, sure, we can do it. We can find 5 or 10 buildings around the country that have done it. Let's just go do it. I think it clearly is technically achievable, but it's not financially viable, and it's probably not the right thing to do if the building that you start with isn't a very efficient building. So the simple message here is the second line down, the net ZEB. What we should be doing is looking at 60 to 80% savings first, squeeze all the efficiency out that we can, and then the small part that's left we attack with renewables. And here's just a concept diagram that shows that and shows it over time. This is for one of the DOE programs, that if you can drop the energy use over time, bring up the renewables use, this just shows in 2020 they're crossing, and you're at that net zero there. The line at the bottom there is another example. If you want to meet these aggressive goals for 10 or 20% of carbon, you could reduce loads by roughly half, reduce the energy needed to meet the loads by half, make things twice as efficient, and then for the remaining energy use, supply it with a source that has only half the carbon content of the existing one. So there are scenarios to get down to these very low numbers, but they're very aggressive and challenging. This is a slightly complicated slide, but it tries to show in the buildings world that you need to pay attention to issues like building size and climate. It's relatively easy to do a net zero building in a small building in a mild climate, and that would be shown over on the left here. On the left-hand one, it would take just the orange amount of money, which isn't so much. But if you were to try to do this for a large building on the right-hand side there, it would cost a lot more. The other way of looking at this is to say, what if I want 70% savings, which is that green dotted line? I can get 70% savings with a modest investment in a small building in a mild climate. It will take a lot more on the right. So this is very much a climate type dependent situation and a building type dependent situation. And because of this, sometimes it's useful to think about the breadth and the depth of the impact you can have. So on the left side of this chart here, we're showing in the upper left there a building, a kind of narrow and deep. This would be a one-off building, a net zero building where you can demonstrate that it really works. On the right-hand side, in the lower part there, we're looking at broad impact potentially. These are the ESCO's energy savings contracts that typically save 5 or 10% in each building, but they use technologies in the market. It's relatively cost-effective. You can think about deploying it widely. Where we want to be in order to get the carbon savings and energy savings I talked about is in the upper right-hand corner. So we need to figure out, again, with technology and policy, how to do the breadth that the ESCOs get today with small savings, but do it at much, much greater impact. That's the challenge. So here's one way of looking at the challenge. This is a scale of building, this is the commercial sector, building energy use. In the top there, that 90,000 BTU, 90 kBTU, we've got a mixture of all kinds of funny IP and SI units here. This is a 90,000 BTU per square foot. This is the average use of commercial buildings in the United States today, averaged over the entire 70 billion square feet of stock. If you were to magically build all buildings to current codes, that's the next circle down. That's about 70. That'd be about 25% better. If you look at where very good buildings are working today, that's in this 40 to 50 range, about half or a little bit less than half. You get skilled designers, an owner who puts a little bit more money into it, and operators that follow through. Those are achievable today, although not widely. And where you want to be for net zero is down at the bottom there. That's that 60 to 80 or 80% reduction. It's, again, technically possible, but a real challenge. Actually, I just wanted to point out here, if I look at this distribution of energy use, I've got the 90 marked as the average. But if I go off to the right and I pick one that's 2 or 3 times as much, your first instinct might be to say, let's see, I'm wired up here, right? That, that's a really inefficient building. It uses 3 times as much as that one. But that could be a data center. And that could be, if that's a data center, that's probably a really good number. If it's an office building, it's a lousy number. So you need to know climate, building type, and size before you can begin to infer whether these are good or bad. And there's been a lot of interest now in looking at how things perform in the real world as opposed to design. This is a project done on some LEED buildings, the U.S. Green Buildings Council LEED rating system, looking at the levels of performance, of measured energy performance based on what LEED rating they got. And, it's somewhat comforting to see that as you get to a better building, a gold or platinum building, the energy use goes down a bit. What's interesting is here's the national average of all buildings. And these, by the way, are pretty much all office buildings. There aren't any data centers in here. And you see that about a third of the buildings that got these good LEED ratings aren't performing even as well as the national average. And some of them, of course, are doing quite well. So the issue is why, of course, putting my research hat on, why is that one up there? Is it poor design? Is it poor installation? Is it poor operation? And why is that one down there? How do I replicate that, and how do I avoid that? One of the things we do a lot of work on at the lab is we develop tools for architects and engineers. And this shows, this plots the calculated designed impact versus measured. And if design always met measured, you'd be on this curve here. What you find is you actually get better performance than predicted out here. But as you try to get better and better designs, lower and lower energy, the actual performance tends to consistently lag the predicted performance. If you're a building owner, that would be a bit of a problem. If you were trying to do a financial deal based on that, would be a problem. So we're fundamentally a research group, and we look at the kinds of issues and problems I've been talking about and say, well, what is it we can do about that? So there's a variety of classic R&D. Let's go invent a disruptive technology that solves some of these problems. We do a lot of real-world demonstration to get out there and show what works or doesn't and why. And so our view here is that the role of R&D is to facilitate this change, but to do it in a variety of different ways. And we work in the area of materials and components. We work in the area of integrated systems. We do tools, and we focus a lot on what really works and why. And I'm going to give you some examples of this. We put together some lists here of what are some of the breakthroughs, R&D breakthroughs, that might make achieving these high performance levels much easier. A set of materials and systems on the left, but balanced by a set of kind of operational issues on the right. And we give them equal weight. I want to be clear that there's lots of opportunity. A lot of people approach this from, if I can just invent a better light bulb, the problem gets solved. You need to put equal weight on the operational issues on the right there to make all of this work. On the research side, there are interesting issues of scale. In this case, we're looking at both time and length, the dimension. So we study and look at things that happen at the level of a room at the meter scale, and we look at things that happen at the whole building scale. And there are interesting issues of time that I'm going to get to. I'm going to talk more about that later, so I won't get into it here. But looking at the issues of heat transfer, looking at the issues of airflow, air and mass flow, looking at issues of communications versus power transmission. Interesting to sort of look at problems this way and look at what insights it gives you into what to do. Integrated systems. There is opportunity in components, but there's probably more opportunity to get the components arrayed into systems that work right. This is just a concept diagram with lots of pretty pictures, and the same thing over here. But you begin to look at how things fit on the integrated systems piece, and then we look here at the design part, what we're calling here a design platform and an operating platform. And the slides I showed you earlier made the argument that there's a big disconnect between the platform on the bottom, the design piece and the operating piece on the right. I'm going to give you some examples now of some projects we've done. We've tried to take these concepts or principles and apply them in the real world, and I'm going to talk about some of the work in the glazing, facade, shading, daylighting area. First of all, we've done some interesting calculations to say if you could magically convert all the windows in all the buildings in the U.S., actually these are commercial, into much better products, what would the impact be, the national impact be? And this shows you that you actually get the envelope of the building itself to become a net energy supplier. I won't get into the details. We've written full papers on this, what technology it takes, how would you use it, how it performs in different climates. This idea of efficiency being a source, which is underlying it, is something you can't read the date up there, May 1988. We did this little brochure that showed if you build a coating plant that coats energy efficient windows, and you sum up all the energy saved by those windows, it turned out to be equal roughly to an offshore oil platform. And so again, as a nation, people underestimate and underappreciate the magnitude of the savings possible through efficiency. So if we look at this issue of technology in the glass and windows area, there's a variety of different things that you want to do or invent or develop that tend to be climate specific, that sort of goes through here, heating, cooling, lighting, daylighting. I do want to make another comment about the renewable side, and this is a balancing act, and I'm not pro or against anything. But if I take sunlight and I convert it through PV to electricity and run it through a lighting system like the one above your head and get to the net use of power of sunlight in the room, you get about 2% efficiency. 2% of the light on the top of the building ends up providing useful light here. If I do it through a skylight, I get about an order of magnitude greater, about 25%. If I do it through a window, I get maybe 3 or 4 times greater. So this is not an anti-PV statement. It does say, though, if you're using PV to to light a one-story office space that could have skylights punched in the roof, you're not making a very good economic judgment there. Skylights won't power my laptop or your toaster oven or things like that. So there's plenty of important use for PV. It's a question here of doing the right thing on efficiency first. There's all kinds of technology for this daylighting stuff too. This is a Japanese system that tracks the sun and funnels daylight through Fresnel lenses into fiber optics and beams them down. It works. I've seen it work. It's just about 2 orders of magnitude too expensive to be scalable. And so one of the things that changed for me in the last 20 years, 20 years ago, we were looking at what can you do? And now I look still at what can we do, but then I always say at the end, and is it scalable? And if it's not scalable, quite frankly, we're a little bit less interested in it than we were before. So this is one of the ways that we kind of think about the research, the opportunities in research, and how to take that research out into the field. So this is an example of what we call smart window coatings. These are coatings on glass that change from transparent to clear. From transparent to either reflective or absorbing. So there's a material science component to this. We have labs there where we invent new materials. We've invented and patented and licensed materials to other people. We work with the manufacturers because it's great to make these little samples at 2 inches square, but if you can't make them at 2 meters square and make them at low cost, you're not going to have impact. So we work with the manufacturers to make sure that what we're doing here ultimately can be made at scale and cost here. We then look at what we have an optical coatings lab that we make available to industry to characterize all this stuff. We have simulation tools that allow you to say, if I take this glass and put it in a window frame system and then put that window system on the 4th floor of this building facing west, how will it perform? And we eventually go out and look at the human factors. We go out into the real world in test rooms and real buildings and look at human factors and make measurements. And it's that combination of activity that ultimately is needed in one form or another. Doesn't all have to be done by one group, isn't all done at one time. But basically, if you don't address that range of activities, you're going to have trouble making the impact that we have. So this is an area where we put these pieces together, and we've actually had for about 10 years a program. We call it different things. This slide happens to say Smart Skin. But this is a program funded by the Department of Energy, by the CEC Peer Program that funds work down here as well. And it tries to bring together a lot of the different pieces and parts to make a system that will provide comfort, performance, and big energy savings. So we go back and say, well, how big are the savings? This is a daylighting example. This is an office building in Emeryville. A before and after. This was a retrofit. So we measured it for a year. These are the days of the year. Measured the lighting energy for a year. The lights were on in the morning and off at night, and pretty much the same. We put in dimmable lighting controls and measured anywhere from 40 to 60% savings on one side and 40 to 80 on the other side. Interestingly, the bigger savings were on the north side, not the south side. That was counterintuitive. There's more sun, there's more light on the south. But it turns out there's also more glare. What do people do? Behavior. People pull the shades to control glare. So you pull the shade in the afternoon. Do you open it up at the end of the day? Do you open it up the next morning to capture the daylight benefit? Not necessarily. You're probably not paid to be a shade manager. You're paid to do some kind of productive work. So this work, by the way, was done in 1990. So this is 20-year-old work. And after 20 years of promoting this and talking about it, dimmable lighting that captures these savings is still only a couple % of the marketplace. So it goes back to my comment that you need to do it, make it work, show that it works, but you need more than that. Now, this whole area of load management, demand management, energy savings in lighting and cooling is critically important because in California and most of the country, something on the order of half of a typical summer peak is driven by cooling and lighting. And with the things we're talking about here, by controlling the cooling load at the facade, by controlling the lighting, we can impact these on the order of 1/3. I mean, just a sketch on the right there obviously is dependent on details, but very, very powerful. And the problem is I go to an engineer and I say, look, if you do all this stuff, you'll reduce your cooling load. Why don't you specify a smaller chiller? Well, no engineer is going to do that because someone says, well, let's hope that everyone pulls the shades in the afternoon. So we have tended to go in the direction of automated systems to reliably capture the benefits of some of this smart technology. And we get lots of pushback from that, quite frankly. I was saying to someone before, I used to say, well, you know, we know it's possible. Look at the Prius. You know, it works in the automotive world, but now I'm not going to use the Prius example for a while until they fix that, right? So integrated systems, again, is important. So we built this facility at the lab. This is 3 side-by-side rooms where we can install real hardware and test the actual performance under realistic conditions. That's the outside. This is the inside. This is set up. It can be set up in its experimental mode where it's filled with sensors and you can hardly walk through. And then we clean out about 90% of them and we put people in here. And we let people either work under the automated system or give them manual control and look at what happens both in terms of satisfaction and energy savings. Just an example, this work is largely funded by DOE. This is the conference room of the Assistant Secretary for Energy Efficiency at DOE, the highest ranking person in efficiency. And we convinced her to, actually she wasn't there when we did this, it was the prior one, to allow us to put this stuff in that office. And so here it is in operation. It dims, this is fully dimmed. This is the lower one dimmed, the upper one open for daylight. This is interesting. This is something we learned from our field test, and maybe you say it's obvious, but it wasn't at the time. If you control this for glare, it goes to 3%. At 3%, the room is so dark, the lights are on all the time. And so what's the way to, I've got a balance here. Do I want to save cooling energy or lighting energy? I want to optimize. And so we built control modules that will optimize for total energy, for peak, for comfort, and you get different results in terms of how to drive it. And that was one of the things that we're sort of beginning to look at here. So we have this concept then of smart controllers that take inputs from a variety of different engineering and other means. And based on what you want to optimize, and it may be different for different people in different times, it will control a dynamic window, it will control a lighting system, and then drive building performance with a closed loop here with the energy information systems to come back and tell you what it's really doing. We operate lots of interesting facilities. This is, notice the snow in the hills. So this is not Photoshop. It's not the Berkeley Hills. This is Reno, Nevada. We built this and moved it up there. We haven't actually used it recently. For a variety of reasons, but this made highly accurate measurements on real products under realistic conditions, and if you want to test things in winter freezing conditions, you'll wait a long time to do that in Berkeley. This is the facility I showed you before with the electrochromic windows. Now it has automated shading. The business decision there was there's only one manufacturer of electrochromics in the country. It's an expensive product. We want to push the idea of dynamic facades, dynamic shading into the marketplace. There are many manufacturers offering shading systems. And so we do this testing here. In the room on the right is the base case with an interior blind. Interestingly, there's a new building, a new dorm going up on campus, and the architects proposed to use an external shading system. And I heard just last week that it got value engineered out. So you might have been a site for one of these interesting new systems. These are widely used in Europe, been there for 20 years. They work. They're a bit expensive, but they're hardly used in the US, and we're trying to promote that. We also, looking inside the space, so this is a blind. I mean, this isn't rocket science. So let me go back. The electrochromic coatings, that's rocket science. That's cutting-edge material science. It's a tough problem. Patents. It's an interesting challenge that was still with us after 20 years. These are blinds, Venetian blinds, basically, with cords and straps. And this clever blind simply operates the upper part a bit differently than the lower part. It provides better glare control here, lets in enough light to keep the ceiling bright. I mean, that's not a Nobel Prize-winning solution, but it works, and it could save huge amounts of energy. And this is some stuff we're trying to capture the qualitative aspect of the environment at the same time to make sure that we want to drive the blind in a way that makes sure that there's never glare, unacceptable glare on the computer screen on the workstation. Some analysis, and the message here is that many strategies get you good energy savings, which is the green, but only some of them give you good glare control, which are the automated systems. So our experience is we needed the automated systems in order to capture that. And making the business case for this, what we're trying to do here, looking at the system, is to say, instead of just saying, here's my room system, it costs a certain amount of money, it saves a certain amount in heating, cooling, and lighting, I divide the two, I get a payback. What I want to do is go outside this and look at the decisions about facades and lighting here impact peak cooling. Peak cooling drives chiller size. Chiller size is a big investment in buildings. And furthermore, chillers and lighting between them drive power investments, either in a central power station or on site. So what I want to do is I want to invest intelligently a few extra bucks here on that dynamic coating or the shading system. And in the end, I want to save money on the right-hand side. And if I can figure out a clever way to move the money around, I can pretty much pay for a lot of this stuff by taking it out of there and there. Now, that's easy to show from an engineering side. It's quite complicated to make it work in the business world. And why is all this money stuff important, and why have I talked about glare and comfort and so on? Because look at these crude numbers here. You know, approximate, but I think they're pretty good. Energy is on the order of 1% of the value of labor in spaces. Where do I get this number from? Now, a lot of you are students, so maybe you're not making a salary, but those of you that work for a living, take your salary, multiply by 2, that's all the overheads that your company pays, divide by the square footage of your office, and that should be the number. Actually, this is in meters squared, just so you don't panic. I have a metric version and a IP version. So if your number, when you do this in your head, is much higher, either you're overpaid or your office is too small. And if the other way, if the number is too low, then you should ask for either a bigger salary or a smaller office or whatever. Okay, so let me now go from the test facility world, where we've gone from calculations and inventing coatings at the level of a lab to some real-world integrated system, or to an integrated system in a laboratory environment. And now I'm going to go to the real world and say, can I convince anyone that invests money in real buildings that this stuff makes sense? This is the New York Times building. They came to us 5 years ago and said, look, we just hired a European architect. They've given us a beautiful all-glass building. Now, that's a side discussion. Should they have done an all-glass building in New York? But anyway, all-glass building with some external shading. They said this building can be daylit, capture lots of daylighting savings, and they're doing other interesting things, underfloor air, many interesting things. But they said, we want to make sure that the work environment, that A, we capture the savings, and B, the work environment is conducive to people seeing their computer screens. Can we do an automated shading system with dimmable lighting? And they went to all their consultants and they said basically, no, you can't, and even if you could, you couldn't afford it. Well, they actually saw some of those studies I showed you before. They flew a team of 12 people out in the corporate jet. They spent 2 days with us, and we convinced them that it was possible to do it, but that they'd have to work really hard. And what we convinced them to do was to build a mock-up. This is a 5,000 square foot piece of a floor plate. That's the floor plate of that 52-story building. In that mock-up, we fitted out completely interior with different types of shade systems, different types of lighting systems. We developed all kinds of new instrumentation to monitor the glare on the screens of the computers, and we obviously measured all the energy stuff. And after a year of testing, we sort of addressed, all of these different issues here. The interesting thing we did was not to pick the winner and say, okay, shade A wins and shade B doesn't, but to develop a performance spec, which we then bid back out into the marketplace. Now, we've done this kind of thing before. We said this is what should be developed. But frankly, the market doesn't pay much attention to a researcher at a university or national lab saying, oh, gee, it would be nice if your dimmable ballast had a dolly addressable system, But when an owner says, I own a 1.5 million square foot building, I'm going to buy a lot of this stuff. Guess what? The manufacturers pay attention. So they actually developed brand new systems that met this new spec, which their existing systems couldn't do, in less than a year. We put them back in the facility, tested them, verified that they worked. We actually built commissioning tools as well to make sure they would work. And the building seems to be performing quite well. This is as built. It was occupied 2 years ago. A picture in the building. Shades are down here. The lights are off here, and they start to dim back up here. They've published... The manufacturers published data that says 70% savings. This is a building across the bay, San Francisco Federal Building. Again, interesting and complicated, but 12 floors of this building have no mechanical cooling. They use natural airflow at night when the air is cool. Windows open automatically. The airflow goes across the exposed concrete ceiling. It stores the cool. A lot of sophisticated CFD modeling here, airflow modeling, design. A systems integration issue again. If the sensors don't do the right thing at the right time, the building doesn't work, and there's no backup here. There have been some issues getting all this to be right, but I give GSA a lot of credit for trying it and for pushing forward, and the whole design team for getting engaged here. Lighting is a huge opportunity. If you don't pay too much attention, the answer you probably think is LEDs, right? LEDs are going to solve the world's problems, and they probably will. about a decade or two into or maybe a decade or so into the future. They exist today. They're getting to be as efficient as fluorescence, although they're not quite there yet, but they're very expensive, and we have a lot of experience with things that are efficient but expensive, and they don't penetrate the market. In the next decade or so, the real push in lighting needs to be looking at controls, sensors and controls, and that fits quite nicely with the whole I for E theme. Lots of opportunities here. Could talk for an hour just about this stuff, and I won't. We've been doing studies that show, again, 50, 60, 70% savings with smart controls, a huge opportunity. So that leads me logically into the last piece here, which is the whole smart grid thing. And a lot of you are actively involved in this, so don't need to say too much. There's a lot of moving parts here, and this tries to show a few of them. We're particularly involved at the lab in the demand response area. This maps nicely to the work that Gaiman and I4E and CITRIS and all you folks are doing here. Marianne Piet leads this effort. We've done a lot of work with energy information systems to try to extract useful information. This is a kind of a schema that shows that the demand response world and the monitoring world and then the exposing the performance of things to the real world is important here. This deals with the issue of feedback and time frame. I'm going to skip that and just go on to this one, which shows you that if you can control these loads dynamically, if you can control them very quickly, you can get to the sort of the end here, the spinning reserve. I've got a megawatt of lighting in the New York Times building that I can ramp down in maybe it's not milliseconds, but in less than a second. So there's some intriguing things you can do when you now have things wired in networks and controllable. And then there's a time frame here that goes back to daily or monthly energy efficiency. One of the intriguing things we saw with the demand response work is people did this stuff for 4 hours on hot afternoons. They said, gee, I could do this all the time. So something that was a demand response strategy became an energy efficiency strategy. But the theme here basically is to have more information accessible to the facility managers and operators than is currently there. The old paradigm is you get a bill once a month and you struggle to look at what one number means. And the new paradigm is you've got real-time information at a distributed level, at a systems level, and you can tell what's going on at the subsystem level, and if it's going fine, okay. If it's not, fix it. I'm saying that as if it's trivial to do. It's not. It's complicated, but it's one of the things where research is going on. Not just research, where it is being deployed in the real world, and Carl Brown and CIE are doing a lot of interesting work in the campuses to deploy and make these things really work. This is the concept for the DR world, where the utilities send a signal to the owner. The owner gets to decide what's done, but doing the automated infrastructure, an open system, open demand response, is something that we pioneered and seems to be working. I think in the interest of time, I'll skip that. I'll just show you that we go back and measure things in the real world, and when the signals go on, you're saving 10% or so of the energy. So it works. It's been deployed now in hundreds of buildings. People are beginning to make a business out of this. There are companies that have been set up to go to a building owner and capture these savings for them. Just wanted to conclude here with two sets of things. This is a messy, complicated slide that talks about measuring building performance, which is where I started. And I want to show this because we just won an award for a national user facility in buildings, the first one we've ever had in 30 years, which is to look at this integrated building systems issue that I've been talking about piecemeal, but to look at it in a much more integrated way, tying components into systems, individual systems like heating, cooling, and lighting into an integrated building system. And I think what I want to show here is that we have this funding to build a series of these test beds that will look at different systems, skylight systems, HVAC, building controls, intelligent controls. There's a lot of opportunity here to collaborate and integrate with the research agendas and activities down here. And there's a simulation side of all this as well as this. This is going to be done up at, I think I had a picture of it. If any of you have visited the building that I work in, Building 90, we're going to try and replace some of the old trailers out front with these facilities. We're going to eat our own dog food, I guess is what the expression. On the third floor where I live, we're going to retrofit the entire floor and put all this stuff in and see if it really works. And on the top floor, we're going to do a series of test labs. So this could be pretty exciting over the next year, maybe. And as a user facility, people can come to us, researchers here can come to us and say, gee, we'd like to test some new concepts and see how it works. So what does all this mean? In the basic science world, they talk about grand challenges. understanding the origins of the cosmos and understanding DNA and quarks and so on. So I think there's a grand challenge in the buildings area with 3 or 4 or 5 parts. One is making the performance visible and actionable, and that gets into the whole EIS and a lot of other stuff I talked about. Focusing on the whole life cycle of the building, making the links between the design part, how you design it, how you build it, how you operate it. Looking at the building as a system, you start with materials and devices, but you need to end up with looking at the system's point of view. And then to really make anything truly happen, you need to have this intersection between technology, policy, economics, business, behavior. There's a whole cluster of things where the behavioral part is an intriguing one that historically has not been looked at very closely, and there's been a lot of new interest in work, and there's collaborations in a variety of departments here on campus in the lab to try to look at this. The concept isn't new. I mean, there's a classic study from the 70s. Carl, when was the Princeton study done? 74, which said if you measure energy use in 200 apartment buildings, it varies by a factor of 5 to 1. The apartments are identical. You get, I think, a 5 to 1 difference in energy use. So the concept that behavior drives energy use is not a new one. The issue of what do you do about it? Once you understand that, how do you deal with that? And as someone who's been working on this stuff for 30 years, you need to be a little proactive. In terms of making performance visible, there's interesting stuff going on in Europe. All buildings have ratings and labels. We're starting that in California. We're developing some benchmarking tools that are interesting. This stuff is all web-based you can look at. This is that life cycle theme I talked about. The issue here is if you're going to do stuff across the life cycle, you want a common data model, a building information model. This is slowly but surely transforming the industry. That's interesting. I guess it's telling me that my time is up now. But it is. Let me just, I have 2 more slides if I get to them. And if I don't, that's okay too. That was this. And so the other thing we try to do is we try to go after this at 3 different levels. There's a piece of me on the research side. I like to do the really breakthrough innovation stuff. But if we're going to save the planet and reduce all those quads of energy, we need to be working aggressively at these other scales as well. Deploying the stuff that we know works now and is underutilized. There's a huge amount here. Voluntary programs, mandatory programs, the cutting-edge emerging technology stuff. I showed you some examples of that. The New York Times would be an example of that. And then doing the R&D. And over time, this stuff ideally migrates here, and this stuff ideally migrates there. And that's actually happened. You can see that. And just to emphasize this point that we aren't going to get it done if we don't put all the pieces together. The old stool is going to topple over if some of that is missing. And people have spent some time thinking about how you put these pieces together. Standards cut off the back end of the problem. R&D, so this is an efficiency scale here. R&D pushes the boundary out here. Standard says you can't make a refrigerator that's less than some level, and you have a whole lot of energy star things and voluntary activities and incentives and rebates in the middle. And collectively, if there is, in fact, an energy policy at a state or national level, you're pushing that forward. So 2 hopefully uplifting slides here at the end. This is a win-win-win. We do the right thing for people, and in the end, buildings are about people. I can save 100% of the energy in this building by simply turning everything off. So that's not the direction we're going in. But I think you can do the right thing for both the owners and the occupants, and if you do that, you're probably capturing the planet. And then a couple of quotes that have stuck with me. As researchers, we're always asked to go to the market and find out what the market wants. And we do that, and that's important. But I think this is important, too. You have to ask the question the right way. People don't ask for things that they don't know exist. And so if you ask for 80%, if you ask people, do they want 80% energy savings in buildings, they don't know, or they think it's too expensive, you aren't going to get that. So I think this is important. And so we're really about trying to define the future we want and then inventing it, and that's critically important. And again, for someone who's worked at it for 30 years, it doesn't happen quickly. But this is it's a quote from Tom Friedman, but he got it from someplace else. But I think it's the right way to sort of manipulate the world when you can only influence small pieces at a time, and we're tackling enormous, huge problems, and simply let's not wait. So thanks for your attention, and I'm willing to take questions. I'm going to hang around after this as well.
That was terrific, Steve, and it shows just decades of incredible work that's resulted from your work and those of your colleagues. And so we are open for questions, and I have 2 microphones that I can distribute around, and happy to take the first question. Yes, Alice.
Steve, great talk. Really love the photo of you when you were younger. One question I have is, with the new California standards, are they building in actual performance instead of the construction? I mean, it seems to me that's the big flaw in the LEED standards, is that there's no connection with what the actual performance is on the building.
So, and you all heard the question, I think. So the answer is yes. Both the state is interested and concerned that the buildings as built and delivered perform. And the U.S. Green Buildings Council is also interested and concerned. They have implemented in the latest version of LEED a requirement that basically that buildings disclose their performance, and I believe, I may not get this exactly right, that if you don't show measured performance over time, they will take away the plaque or put a black piece of cloth over it or whatever. But I think it's fair to say that the leadership of USGBC understands that there's a problem and they're acting on it. It's not the power of, I mean, what USGBC has done is they've moved the industry in important ways, and that is, my first slide says the industry moves slowly, so we're not going to make a right turn and solve that problem quickly. But they're behind it, and we're the kinds of groups, hopefully that they'll work with to try to build some of these tools and so on that they need. Yes?
So the energy usage per capita in buildings in developing nations is at least a magnitude smaller.
Right.
And they haven't had all this R&D go into it. So would you think that the larger magnitude of savings is through actually changing user behavior, or is it really through building this better? So
that's a critically important point. And I want to say also that the laboratory has a team that's worked in China for 20 years, a pretty big group that works on energy efficiency in China. And we have another group we've started a year or two, which is a joint campus LBL activity called Bijli that works in India. So I would say that here's a case where you have to be careful about the kind of the averages. There's a part of both India and China where they're building buildings very much like what we're talking about here. And a lot of what I talked about is relevant. And we've had collaborations. We've had early morning or late night phone calls with groups in India and China doing these kinds of cutting edge projects. On the other hand, as you're suggesting, there's a huge part of the population that's living in a situation where the opportunity to invest in all this neat stuff is much more limited. And I think I would only say that there are scalable solutions that work for all of them. You're not going to put an automated shade with dimmable lighting in a 50 square meter house for someone in China. But the fundamental issue, which is managing solar control, can be done with other means. The laboratory also, at the other end of the spectrum, Ashok Gadgil, has developed cooking stoves for people in Darfur and water purification. So even at a lower, more fundamental level of just staying alive, the lab has people who are quite interested in helping to meet the needs of the poorest part. And I think it's also true, we all feel quite strongly that we need to, as a rich country, solve the problem here. But if we don't help the rapidly growing parts of the world solve their problems, then we're all going to suffer the consequences. So we're active in both sides.
I actually have a very naive question.
Those are the hardest usually.
No, I've seen European homes, most of the cost is the heating cost. And one of the things I'm seeing is like there are houses in Europe that they have a boiler and they have steam or something that heats the house. So my question is, what is more efficient? Is a boiler or a furnace that heats the...
Okay, so in Europe, most of the houses do have heating loads because they're in a heating-dominated climate, and that's not quite as true in the U.S. There's a movement in Europe for something called passive houses, and the idea there is to make houses that frankly don't need boilers. If you make the envelope so tight and so efficient, and you manage the shading and all that, you can get to the point where literally the internal loads of the house, the people, the appliances, more or less balance the heating load on a cold winter day. So, but if you're talking about an existing building, what the Europeans are doing rather aggressively is they're re-insulating a lot of buildings. They're going and doing external, I mean, if you've got a 50 or 100-year-old brick building or block building, they're doing external insulation, they're doing some internal insulation, they're trying to reduce the loads first, and then the issue of which heating or cooling system to use, that's going to be case by case, I think, in terms, what's the fuel supply? Do you have gas available? Is it bricks? They're doing a lot with pellets. Wood pellet heating is another area. So there's a lot of different issues. Whatever the system that you end up choosing, you want that system to be engineered and designed to be efficient. And part of that, by the way, is how you distribute the heat. If you've got a big house and 2 people living in 10% of the space, you don't want to be heating the whole house at the same time, so it becomes a controls problem again. So there's a bunch of different dimensions to that naive question that are all interesting to pursue.
Maybe we'll take just one more question, and then we're going to have to cut it off.
This is another naive question. I've noticed in the last 30, 40 years that refrigerators in the old days used to last about 20, 25 years, and I'm noticing the new ones are lasting 10, 15 years. We had a 1947 heater in our Victorian home that we just changed for a more efficient heater that's got maybe 10, 20 years of lifespan. And also the flat TVs have half the lifespan of the old CRTs. So, I mean, what price are we paying for greenness? I mean, or am I wrong about the observations?
Well, let me go the other way. I'm not sure you're right. I don't think there's anything intrinsic about those things you mentioned. And there's no reason why a new refrigerator can't last as long as an old. My experience has been that they're pretty good. I mean, frankly, it depends partly on what the manufacturers choose to do and partly on what the market says it wants. We do tend to be to live in a society where the paradigm is consume, and therefore, if the expectation is that that people will want a new refrigerator every 15 years because of the style, then why bother engineering it so it will last for 30? I'm not sure that's the logic that goes into it, but there's another interesting twist to that is if you're dealing with a product where energy use is improving rapidly, maybe you want a short lifetime. I mean, the other piece of this is that I've talked only about operational energy. There's an embodied energy life cycle assessment. There's a whole very intriguing area of life cycle assessment or analysis that looks at the cradle to grave or cradle to cradle impacts of building and using something. The typical number in buildings is only about 10% of the life cycle is the embodied stuff. So the message crudely is pay attention to operations. But for other products, it could well be that a lot of the issues are embodied energy, manufacturing costs, transport costs, and you need to pay more attention. So I think what you'll see is you'll see people paying more attention to those issues. Maybe those will show up in ratings and labels, and then maybe that will ultimately drive what the manufacturers choose to do. I'm sure you could find data someplace that might show you the average lifetime of these appliances, but I don't know that myself.
Steve, thank you very much. I'm sure he'd be happy to stay around
Yeah,
for
I will
anyone
stick
that wants
around,
to come
sure.
down and talk to him later.
Yep.
That was terrific.